Welcome to This Explainer. Today, we're diving into an absolutely crucial concept of process control. Honestly, it's the one thing that really separates the amateurs from the true Lean Six Sigma black belts. If you're out there measuring, analyzing, or trying to improve processes, you have got to understand the fundamental difference between simply summarizing what already happened and mathematically predicting what is going to happen. So get ready, because this methodology is going to completely change how you look at your performance dashboards forever.
Right off the bat, I really want you to listen closely to this thought. Many managers make the exact same fatal mistake. They look at a graph with historical data from the past month, they see a nice, clean average, and they immediately conclude that their process is perfectly stable for the future. But guys, that is a dangerous misconception. Summarizing past data is something completely different from predicting, with mathematical certainty, what your process will actually do tomorrow. And that right there, that is the exact difference between descriptive and inferential statistics.
So let's dive right into this fatal management mistake and why those historical averages deceive us. Relying solely on past snapshots is a trap, and it gives you a totally false sense of security.
To understand why, let's look at our first major concept, descriptive statistics. This is all about looking back and analyzing what already happened.
Think of descriptive statistics as your way to organize and visually summarize the data you already have sitting in front of you. We're talking about measures of central tendency, right? Things like calculating your mean, just adding up all the observations and dividing by the number of observations, or finding your median. We're also looking at measures of spread, like the range, taking your highest value minus your lowest, and the standard deviation, which just tells us how much our values typically bounce around from that mean. We visualize all this stuff with histograms and box plots, but here is the massive catch. Descriptive statistics go no further than the sample you collected. They describe that sample and literally nothing else.
To really anchor this, let's look at a practical, real-world case. Imagine we're working together at BlueprintRM&co, which is a high-end e-commerce logistics company. You're stepping in as the acting black belt, and we're currently in the measure phase. Our big goal? We need to analyze the processing time at our main packing lines. We have to know exactly how long it takes to pack an order so we can actually meet the delivery promises we're making to our customers. So, you head down to the warehouse floor and you take a sample. Out of 500 measured packages, you calculate that the descriptive average packing time was exactly 75 seconds. Management looks at that 75 seconds, they smile, and they think, "Awesome, our process is totally stable."
You dig a little deeper into those descriptive stats and find out the standard deviation is 5 seconds. You plot it all out and wow, it forms this beautiful, neat, bell-shaped normal distribution curve. Most packages take somewhere between 70 and 80 seconds. It looks perfect, right? But let me remind you again, this only tells the story of the past. It tells us the exact reality of those specific 500 packages you watched. It does absolutely nothing to guarantee that the next million packages will behave the exact same way. And this brilliantly illustrates the core transition every single process improver has to make. If you look at the left side here, descriptive statistics focuses strictly on the sample. It summarizes the past and shows you exactly what happened. But look over at the right side. Inferential statistics focuses on the entire population. It predicts the future. It uses the complex math of probability. This is that massive leap from looking backward at a limited little sample to looking forward to confidently predict how millions of future e-commerce orders are going to behave. Which brings us to the real hero of our story, inferential statistics, and looking forward to get mathematical certainty for the future. To actually achieve that forward-looking certainty, we need some specific tools. And the most essential one a black belt uses is the hypothesis test. You can kind of think of this like a statistical trial. We set up a null hypothesis, which usually just says, hey, there's no change or no difference here, and an alternative hypothesis, which argues that there is a structural change. The hypothesis test determines if an effect we observed in our sample is actually structural and true for the whole population, or if it was just pure coincidence. It's literally how we mathematically prove things. And the ultimate output of this test, it's the p-value, or probability value. This is the metric we use to calculate the exact probability that a result happened purely by chance. In Six Sigma, we usually use an alpha level of 0.05 as our standard. Basically, if our p-value is less than 0.05, we have 95% mathematical confidence that our result is statistically significant. It gives us the confidence we need to validate assumptions about the entire population. When that p-value is low, the null hypothesis has got to go.
Let's bring this right back to our practical logistics case and see how we'd actually validate a new scanning technique.
Imagine the team rolls out a brand new scanning technique on the packing line. They measure another 500 packages and, hey,
The new average time is faster. The descriptive statistics show a clear improvement. But here is the critical question I have for you. Is that new scanner actually structurally faster? Or did that specific 500 package sample just get lucky? Maybe the workers were just highly caffeinated that day, or the packages happened to be smaller. If your management makes a $1 million decision to roll this scanner out globally based just on that descriptive average, they are taking a massive gamble.
To build a rock-solid conclusion, you'd walk through this exact methodology. Step 1. Measure 500 packages using the new scanner so you have a representative, independent sample. Step 2. Run a hypothesis test. Since we're comparing averages of continuous data here, we'd use a t-test to mathematically compare the new scanner data against our old baseline. Step 3. Calculate the p-value. If that p-value drops below 0.05, you have mathematically ruled out coincidence. You've officially transitioned from a simple basic sample to a verified conclusion for the future.
So the crucial point is, why do we even go through all this complex math? It's about deciding without noise, which is the ultimate strategic goal of Six Sigma.
Let's break down those strategic benefits. First, you completely eliminate the risk of making organizational decisions based on noise. You know, those random daily fluctuations that descriptive stats just can't filter out. Second, you can actually predict your future process behavior with mathematical certainty. And third, you can continuously control your process within the upper and lower specification limits, ensuring that what the process does perfectly matches what the customer actually wants.
It really all comes down to this single, undeniable truth. Without inferential statistics, Six Sigma remains totally stuck looking backward. Summarizing what happened yesterday is fine for a quick status report, sure. But inferential stats are the absolute only way to mathematically control your process for tomorrow.
I really hope this explainer has completely shifted how you view your data. The next time you open up a dashboard, I want you to ask yourself, are you just admiring the past, or are you mathematically controlling the future? Keep testing those hypotheses, and as always, for learning and entertainment.